Dobry den, Boyan Krosnov.
Hi there.
Welcome, Boyan. Boyan is one of the founders and the CPO of StorPool Storage. He will talk about benchmarking cloud performance with the top 4 cloud providers. He also will enable you to estimate your market position correctly to perform better than the cloud giants. Thank you very much, Boyan. It's your stage.
Thank you. This is my topic for today, and I prepared. Let's see how to do that. Okay, so I've prepared a presentation on this topic, and here's some information about me. I'm the chief of product of an SDS company called StorPool. I'm one of the co-founders, and I've been working in the kind of internet service providers and SDN and now SDS for more than 20 years now. And my focus area in IT is IT infrastructure, specifically inventions in that area and performance and efficiency. Here's a bit about our company. StorPool is an NVMe software-defined storage system, SDS, mostly used for virtual machines and containers. It's a scale-out system, highly available, API controlled. We started it in 2011, and it's been in production use since 2013. Nowadays, we're kind of growing quite a lot every year in terms of deployed base. We're based in Sofia, Bulgaria. It's used mostly for virtual disks of KVM virtual machines, but also a little bit for bare metal Linux hosts and also for VMware and Hyper-V and server. And it's one of these, it's the type of system that's deeply integrated into kind of DevOps and SRE environments through API integration with OpenStack and Kubernetes and etc. and other cloud management systems. Why do we think today's topic matters? It's not because of performance for its own sake. It's better performance of your infrastructure gains you better application performance, and that's the end goal of this. And application performance, it is what you define. So it could be the time to load a page, the time to rebuild in a build or a continuous integration system, the time to execute a specific query in kind of a business analytics system, etc. It means happier customers in public cloud as well as private but multi-tenant environments. And there are real money-driven business metrics for better performance that benefit from better performance. For example, if you can deliver twice as much performance for the same amount of money, then you can also almost certainly deliver the same workload with not half, but a smaller fraction of the investment or the monthly spend. So for public clouds, to summarize, performance is important because you can win customers over and you can retain these customers and you compete with other public cloud providers. In private cloud, you're interested in performance because you can do more with less and you can win applications and workloads and teams over from your main competitor, which is public cloud. Here's my agenda now that we know why we're doing this. So we have understanding what performance is, benchmarks of some public clouds, which I think is kind of the main star of the show today, how to measure and optimize your own cloud's performance, and then I have some discussion on total cost of ownership, etc., kind of more monetary metrics, and I have some conclusions at the end. So this is something very important to understand, and I find that it's not widely understood in the IT industry. And this is kind of a throughput versus latency or load versus latency curve of any transaction processing system looks like this. So this could be a storage system, a database, a load balancer, etc., etc., etc. They all have a very similar kind of performance envelope. if you will. So this means that at very low load, you get low latency and the best service. So everything is snappy because the system is essentially idling and waiting for your input, and it responds immediately. If you increase the load, you get a slightly higher latency, and there is some point over there, which is the lowest cost per delivered resource, which is kind of the optimal or most efficient operating point of the particular system. And then the problem with running your systems close to that most efficient point is that the moment you go over the knee, there is only pain. The reason for that is you get a slightly higher demand for more load, and then you get an explosion of latency. And the reason you get that explosion of latency is because of queuing. So if you have slightly more requests than the system can handle, you get more and more requests queued up, and you end up with an infinite queue, right? With just a small increase of the load. And one of the kind of problems with performance and benchmarks is that most published benchmarks work in that part of the curve. The results vendors publish end up representing a part of the curve that you are never going to use, because you're always going to run your application in the lower left part of the curve. You're going to run the system at a fraction of its total available throughput or total available performance. So this is the first thing to understand about performance, and you need to be careful that when you characterize performance or benchmark, you do that in the area of the curve that actually represents your production system, which will be somewhere around here. To give like a so to make sure this is not just like a theoretical exercise, this is an example with a real system, fairly small StorPool storage system. These are IOs per second on a particular test, and obviously, if you get a larger system, you would get a higher throughput. If you use a different type of drive, you would get lower latency, etc. So the exact location of this curve depends on the hardware you use, obviously. But the point I'm trying to make is, if a storage vendor publishes kind of the largest IOPS number they can publish, they'll give you these numbers here, right? However, in your real production environment, you're most likely to use the system in this part of the curve. So you wouldn't use it in that part. So then, does it matter how many IOPS can the system do? Yes, it does matter, but it matters because of other reasons. It matters because of, say, very parallel workloads, or if you need to support thousands of virtual machines and you want to make sure you have enough kind of performance overhead for a very bursty traffic, etc. But for a specific application, what really matters is if we can take this part of the curve and shift it down. So if you have enough, say, IOPS for your workload, changing the latency under load of the system, reducing that 2 times, has a very large impact on actual application performance, right? Because that's the area of the curve where your real applications work. All right, so here are some benchmarks we did on public cloud. So we've been doing these kinds of benchmarks, a very similar set. We've been running them for a couple of years now. And we have a published report from last year on our website, and we intend to update that this year, maybe in the next month. So what we do is we take virtual machines which appear identical in terms of parameters from different public clouds. And the last thing, Catapult is a StorPool customer. So this is like a StorPool based cloud for comparison. So the point here is we take the same amount of resources. If you read the data sheet of these different public clouds, they will all say this VM has 8 vCPUs and 16 gigs of RAM. Some of them have slightly more memory, and what we do is we allocate a part of the memory using a RAM disk to make sure that our benchmarks are not skewed because of the different products that these different clouds offer, right? So we start with 5 identical VMs in terms of amount of resources, vCPUs and RAM. We also purchase from these public clouds a storage volume. In Amazon, this is the Amazon EBS service. And these names are not complete, but this is the Google Persistent Disk SSD, etc. I have the correct names on the next slide. And they're the same size. They're slightly different costs. So some of them are $100, others are $170. And they have different IOPS limits because this is how storage in public cloud works. So for a particular size, you get a particular number of IOPS as a limit, right? And we use a bunch of synthetic and more kind of platform application benchmark tools like FIO and Rsync and pgbench and sysbench to measure the performance of these seemingly identical virtual machines. And what we get is, so first, I started this by saying latency is extremely important. And you can see that there is like an 80 times different latency, or at least 50 times or more different latency under light load of the storage service of these virtual machines. So our customer and friends at Catapult, who have like a StorPool best current practice system, their virtual machines can respond to IO operations in 100 microseconds, right? And if you go to someone like, I don't know, DigitalOcean, you get 3 milliseconds for responding to a single IO operation, right? And this is represented in 2 different ways. One way is the latency itself, and this is the 1 over latency, which is IOPS at very low queue depth. Queue depth is the number of kind of parallel storage operations that are issued. So what does this mean for application performance, though? So this is, FIO is a very synthetic benchmark, and we want to translate this into time to deploy or some other kind of more meaningful metric, right? So in this test, it says there is at least a 3 times difference in latency under light load between our friends and AWS Amazon EC2, the EBS service there. So this is the kind of the first of the application benchmarks. This is the time to resync 3 million files. So you can scale this down if you obviously if you have like a smaller task to do, smaller task in terms of say redeploying an application or something like that. And this gives you a difference of say on one system you can do this in 85 seconds, and if you go to Azure and purchase the type of VM and type of storage that we have, you can do that in 5 times as much time. So it takes several minutes to do something that you can do in a minute, right? And pgbench we use as like a stand-in for a transactional database. It uses PostgreSQL. Sysbench results are extremely similar, so I'm only going to look at pgbench results this time. What this chart represents is latency versus transactions per second. So there is a particular kind of business transactional workload that pgbench runs on top of a Postgre database. And for every kind of particular level of load, which in pgbench is defined by number of parallel clients, it can tell you how many transactions per second it got and at what latency, like what was the average response time for a particular query in the database or a particular transaction individual transaction in the database. So these then end up on a transactions versus latency chart, and every dot here means that pgbench on the Google VM, which we defined a couple of slides back, can do this many transactions per second, which let's say it's about 4,000 at about 4 milliseconds latency per transaction. And you'll notice that after, like if you get more and more parallel clients, you don't get more transactions per second, you just get higher latency because there is a higher queuing latency in there. So you can think of these as the additional clients that you had issued their request, they waited in a queue for some time, and then their transactions got processed, and that's why the latency is higher. So the first, by kind of only looking at this chart, the first conclusion we can get is these services are unfit for databases, and for some of them it's obvious why. For example, Amazon promotes like provision.io EBS service, which is a lot more expensive for the database use case. So you could say Amazon GPU maybe is not what it was designed for. However, when you have services like Google's persistent disk or Catapult's StorPool-based NVMe storage at a similar cost, which is like 50% higher cost, which deliver a lot more transactions per second at a lot lower latency, you can directly say these services are unfit for databases and we should only concentrate on these two. This is a zoom in on the left part of this chart, so say up to 5 milliseconds, I think. Yeah. And here we can see the kind of the gap between the different services. So the Google service which we purchased, which we got, has about 3.5 fewer transactions per second with the same CPU and RAM and essentially the same cost for the virtual machine for the compute. So this tells you that you can get a lot more work done with the same amount of spend if you have a fast storage system, right? And then at the same time, if you have a fixed load, so say in this example, if you have a load which is 2,500 transactions per second, with this system you can get 2.5 to 3 times lower latency serving these 2,500 transactions per second. And there are like many reasons inside of these systems which cause this difference. The kind of the point we're making here is it is possible to beat even hyperscalers and deliver a service on the market which is both price competitive and a lot faster, as our customers have demonstrated here. And the next part I have is, just give me 1 second, how to measure and optimize your own cloud. And let's take this step by step. So first of all, I would definitely not recommend running standard synthetic benchmarks. That is, unless you understand how these standard benchmarks map to your use case and your application. For example, the FIO with a certain number of parallel requests, random reads, random writes, may be relevant if you know this is exactly what your application is doing. And out of the synthetic workloads, the one we found to be most relevant is FIO with IO depth 1, because there are a lot of workloads which are kind of dependent, and they issue an IO operation and then they wait for that to complete and then they issue another operation. So don't measure synthetic metrics, measure what matters to you. So for example, if your a software development company, and you can deliver a certain feature or application with a very simple SQL database for up to a certain number of users, and you can go away without the complexity of clusters, then this is a huge increase to your development productivity, and this is something that you can aim for and you can achieve if you aim for it. And also in that example, the time it takes for your development organization to run tests influences a lot their kind of velocity of how fast they can deliver features. So if you can run your complete test suite in half the time, maybe this is worth something to your organization. So it depends a lot on what your use case is. And then in the main one we see, both in public cloud as well as in private cloud, is efficiency. So these are metrics like dollars per user, or what is the cost to support a particular feature in a kind of microservice architecture, right? In a lot of cases, these really can't be measured directly, so it's just too kind of complex and too hard to extract the metric from the real environment. And in these cases, I would recommend finding good proxies for your real metrics. So, for example, if you know that your application consists of a load balancer and a database, say an Nginx as a load balancer and PostgreSQL as a transactional database, or MySQL as a transactional database, then you should run these benchmarks like an Nginx benchmark and a database benchmark instead of the synthetics, instead of like a core performance benchmark, which doesn't relate in any way to your real workload, right? Specifically for storage benchmarks, be aware that there is a lot of snake oil out there. As I explained in the very beginning, there are a lot of kind of benchmarks which are, oops, sorry, managed to scroll back. So there are a lot of benchmarks which are run with a very high queue depth or very large number of outstanding IOs. And this is nowhere near what like your real production load will behave. And we've also seen things like the storage vendor would show benchmarks with RAM disk because it's faster, because it shows the higher number, but this doesn't relate to how you would use that system in your environment. Let's repeat that one more time. Synthetic workloads don't really approximate real workloads. So you need to be kind of figure out a way to reproduce your real workload as close as possible. If you want to be able to measure, and because you can measure, then you can optimize. This is the idea. So here's some published information from us. So this is the previous version of the tool we use for these kind of public cloud VM testing and testing in the environment of our customers. Are published over there on our website. And we'll be releasing updated tools and methodology in the next month. So the goal is to update this page as well as one more document on our website, which shows the same information we have in this presentation, but in a kind of long form. If you're interested in any of the tools we used, drop us an email on info@storpool.com. However, be aware that these are kind of specific, say, a transactional database benchmark and another transactional database benchmark. And in your environment, your application may depend on a very different kind of platforms or components, which you should benchmark instead of these, right? Then when we talk about, so far this was about measurement. When we talk about optimization, first you need to understand that it's quite likely your existing hardware. So if you have a private cloud environment, it's very likely that your existing environment can be optimized to a very large degree. And my colleague Venko has a talk specifically on that topic for kind of KVM-based clouds and how to get the most performance out of them, which is tomorrow at 11 a.m. Central European. And kind of two things that stand out from there is fast networking and fast storage increase a lot your compute efficiency, meaning if you have a fast storage system, you can do a lot more work on the same CPU, on the same core, on the same amount of compute resource. And I'm hoping that the performance I showed so far should convince you of that. Obviously, our friends at Crystal don't have access to some magical CPUs, right? They have access to the same hardware that Google and the others have. However, you can see these 2 to 3 times performance gains, performance differences that they achieve. And so this is if you have existing hardware, and if you're building a new cloud, you need to kind of optimize for your specific use case. So instead of kind of getting whatever server configurations and whatever CPUs your server vendor proposes, you should really optimize for your use case. And your use case may be different than someone else's use case, say, for example, by the power limit you have in your data center, or how much performance per core, like what is the frequency of the core, how much that matters for your specific application. So if it's very parallel, maybe kind of the gigahertz, the frequency of each core doesn't matter. If it's not that parallel, maybe it matters a lot more. How much memory do you need per core? How much storage do you need per core? And at the end, when you have all the kind of input parameters collected, what you're essentially optimizing is the per core cost of the whole solution. Here are some examples for how an optimization effort like that looks like. This is a table which tells you which Xeon Scalable CPU is the optimal. And you may notice that it's not the cheapest Xeon Scalable CPU. So CPUs that cost like $2,000 come at the top of the chart. And then if you look for a CPU with a particular frequency, then you end up with CPUs which are more like $3,000 per CPU. So the cost of the individual component is not what determines this. It's kind of, it fits in an overall total cost calculation, and then different components are being preferred because of that. This is a public resource. Just drop us an email. We'll share it with you. So these are areas where you could optimize. So the hardware, the host and hypervisor, and for this part, my colleague Venko has a talk tomorrow. Virtual networking, there is also something about that in the talk tomorrow. And then storage, we would say get like a really low latency storage system, and the system we deliver is a system like that. Or you could look for something else that has a similar performance characteristics. Obviously, when you're selecting a storage system, there are a lot of things you're looking at, not just performance, right? So these are the areas where optimization may happen. And in kind of a best current practice system, you end up with a performance envelope which is 2 times or more better than the best public cloud services, right? Just by optimizing for your specific use case. So there was some kind of talk on total cost of ownership, and we promised in the description to give you some ideas on that. So this is the kind of TCO approach, meaning how does it work? First, you need to define your minimum service level. So when you're optimizing cost, you need to make sure that you're not optimizing the costs beyond the level at which it would affect your other metrics. So there is some kind of you may get it you may be able to get something cheaper, but then it breaks a lot, or you may be able to get something cheaper, but it doesn't deliver, say, the same amount of individual core performance, which then trickles down and affects the whole application performance, and you don't get the benefit that you're intended to. So defining the minimum service level is very important, and this is both in terms of performance and as well as availability, etc. And then at the next step, you're trying to get the lowest cost possible for delivering the service level. And you don't do that by the cost of purchasing, obviously. And you need to do that by the total cost of a project, right? And this ends up being a large spreadsheet. So it could have, say, 10 plus sheets and hundreds of lines in each sheet with hundreds of parameters to tune. And what you're optimizing for is trying to find the right settings, or say the right model of CPU, and how many servers per rack, and should I use 10 gigabit or 25 gigabit networks? Should I use this storage vendor or that storage vendor? Should I use KVM or VMware, etc.? So you're testing these different hypotheses in order to minimize your total cost per delivered resource, and you need to define what the delivered resource is. This approach is obviously usable both in public cloud as well as in private cloud scenarios, and I've seen some private cloud environments where this was done really well, and others in which this was not done at all. As well as in public clouds, I've seen places where the servers they got were what was available on the market, and other scenarios, as the example I gave before, where they really ended up with a very good optimized system that enables them to be competitive on the market, right? Here's one example for a TCO calculator. We have this, you can request it on our website. And the yellow fields here are kind of input parameters, and some of these are kind of affect the total cost quite a lot. So you could, one thing, once you have a model like this, one thing you can do is you can play with these parameters, and by that figure out which are the most sensitive parameters, and maybe say, for example, one parameter could be what is the power, maximum power per rack that they have in a data center. And then if you figure out this parameter, your model, cost model is very sensitive to this parameter, you could discuss with your data center operator to give you more power, to like give you a rack in a different location, for example. But which parameter is most important for your specific use case depends on your specific use case. So beware that there is no one recipe that fits all, right? So what to include, what I think you should include in your total cost per delivered IT infrastructure, right? So there is data center, so power and cooling, and power per rack, and remote hands, and security, and like access, physical access, compute, which is servers, and like one interesting way to look at this is that essentially what you want is CPUs and memory, and everything else on the sheet is overhead. It's not exactly like that, but at least in the compute part, it makes a lot of sense to look at it that way. Like what is the cheapest server I can get within certain parameters, so it doesn't break every day, right? The cheapest server I can get per CPU core. And what ends up from that calculation is you end up with CPUs with many cores, you end up with many compute nodes per chassis, etc. So that direction ends up with a very large, high density of compute, because that minimizes the amount of server you have per unit of compute, right? So server CPU RAM, one of the most important parameters is the minimum performance you want out of each CPU core, which translates into frequency, but not exactly, because we have two vendors and the frequency on an Intel CPU is not at all comparable with the frequency on an AMD CPU. So if you have multiple vendors, you need to match them in some other way, which is relevant to your application. Cost for cloud orchestration, so there may be some software you lease or get a license for. And there is also your internal cost for managing the compute part or the whole cloud environment. Then in storage, you have storage nodes and drives and software and cost for managing the storage solution. You also have a storage network in here. And I said here storage servers and drives and software, but these three may be, you may get them as a storage appliance, for example. And this is another approach you could take and experiment with, right? Then in network, you have virtual network CPU, how much space in the rack and power does it use? In virtual networking, how much CPU does virtual network solution use on the hypervisor hosts themselves? Is something that you need to kind of calculate in the cost of the network. Software for doing that, so you could have like service mesh or overlay network software or something like that, and you have your cost for managing this part. Then you also have the public network and IP transit cost, etc. So these are kind of, I think, at the bare minimum components of your total infrastructure costs that you should include in your model. Our example has all of them. And I'm going to my conclusion. So first of all, if you're buying public cloud services and you're comparing between different public clouds, and one says 8 CPUs and 16 gigs of RAM for price X, and the other says 8 CPUs and 16 gigs of RAM for price Y, you can't compare the two prices because you're not getting the same thing from the two providers. You can't judge the VM by its number of vCPUs and memory, unfortunately. And performance and application performance specifically is a lot more complex than that. So the performance of the application may be affected by many other factors, not just the kind of number of vCPUs or their frequency, right? Very important, I think, is if you measure, you should measure what matters to you and not what someone else thinks, because otherwise you you end up optimizing on a metric that really doesn't matter to you, and that optimization might also hinder your deployment, right? If you're public or a private cloud, getting 2 or 3 times or even higher application performance per dollar is within reach. It's not like some dark magic. The things that kind of hyperscalers are doing is not dark magic. It's possible to reach application performance several times higher. And this also, if you flip that coin, the same statement means that it's likely you can get half the cost for the same workload. So if you have your whole kind of application with, so it's a microservices application with hundreds or thousands of, say, containers or VM running in some cloud infrastructure, it's very likely by doing some optimization or it's very likely you would be able to significantly decrease your cost for infrastructure. Yeah. And finally, on your next project, we think you should work with partners who understand performance. Why you should do that is because you can gain a lot by doing so, and gain a lot not just in terms of, say, IOPS and microseconds. That's not what I mean. You can gain a lot in terms of kind of real, tangible business benefits for your organization in terms of, say, cost or time saved for developers, etc., etc. Right. And this was the end of my presentation, and I'm open to questions. Any questions?
Thank you very much, Boyan. So I see there are some questions in the chat. Maybe I can read that for you. And so you can answer. The first question comes from Kay. I run a small, medium enterprise cloud service provider. We do not have much admins. Which cloud management systems would you recommend for a mid-sized cloud service provider? They want to save time and work.
Cool. That's so historically, what has happened with StorPool is we work with many different cloud orchestration systems. So we have a good integration with OpenStack, with OpenNebula, with CloudStack. There are obviously some others on the market that we've decided not to have an integration with. But these are the three that we see in use by our customers. Right. So next, which one should you choose for your specific case? It depends on many factors. So it depends on, as you said, you don't have many sysadmins, so you need a solution that is simple, or alternatively, you need a solution that is fully managed. So it may have some internal complexity, but you rely on an external vendor to manage that complexity for you. Or if, say, for example, you have some internal development resource and these are, they know Python, in that case, OpenStack, if they know Ruby, in that case, OpenNebula, if they know Java, in that case, CloudStack. And this is if you intend to kind of extend and improve the cloud orchestration system, right? So you can approach it from many different directions, and there are many factors that go into that decision. And that decision is a kind of decision with a lot of consequences. So once you get kind of married to a cloud orchestration system, you integrate that with all of your other systems. Unplugging that from your infrastructure is hard to do. So an important decision, definitely.
This is really interesting. Thank you very much for that answer. So I never heard that someone recommended to choose the cloud management depending on the development or coding skills you have. So you use this if you code in Java, or use this if you code in Ruby or something. This is a really interesting approach. Kay also wants to know, he'd be interested in how can he translate the technical numbers you presented into benefits for their customers.
Right. So let's take one example. I'm gonna kind of scroll back quickly. Yeah. So benefits for their customers. So a customer of Catapult may buy. Let's see how much their VMs cost. Here are the virtual machines. So they may get a virtual machine for $120 and put a PostgreSQL database on it, and they can get, say, 10,000 transactions per second on a PostgreSQL database. Whereas if they paid a similar amount of money for a similar quote-unquote virtual machine in Google Cloud, they would only get 4,000 transactions per second. Meaning their customer, by spending the same amount of money, their customer can support more users. Their customer can, their kind of application, their customer's application will work faster, meaning when whatever application it is, it will issue a query to the database, and the database will respond within a millisecond instead of within 3 milliseconds. And these times add up to the total response of the application to the user. The more, so the latency benefit specifically, the more interactive that application is, the higher this benefit is. And the throughput benefit is a matter of load. So if the application only has 10 users and they open it once per day, it doesn't matter at all. But if the application really needs to do 10,000 transactions per second, then this is a huge difference, right?
Okay, thank you. So you're saying also depending on what the goal of the company is, but if my goal is to satisfy as much users as possible, then I have to look into other numbers than somebody who is only looking for highest performance for just one customer, something like that.
Yes, and there is also a kind of I think I've mentioned this once in the presentation, but there is the benefit of simplicity. So in terms of design of your application, if you can solve a problem with like a very simple architecture by getting, say, a larger VM or a large physical server, you would rather do that than architect all the, say, sharding and distribution and fault-tolerant architecture across multiple nodes, etc., in the application. So if you can solve a problem with a very simple architecture, you should always try to do that. And having more performance per VM enables you to do that. It's a very kind of hard to quantify benefit, but it's real and it's there. It's like a benefit for the application developer, right? So if you have like a software as a service, for example, scenario.
Sounds very reasonable. We also have a question from Michael van Veen. Michael asked, what ROE do you think the optimal number? How to decrease the TCO of a cloud without compromise the performance?
It's a balancing act between like defining what your kind of the service level you want to deliver and figuring out what is the cheapest way to deliver that service level. You always want the cheapest, but it's not the absolute cheapest. It's the cheapest for a particular service level, right? Among our customers, we have essentially two groups. One group is trying to do what Catapult does, which is deliver a service at the price of at the price level of popular public clouds, and make sure that service exceeds the service of these public clouds significantly, like it's visibly better service, right? So this is one group that are kind of performance centric, and they have a particular service level, meaning higher frequency on their CPUs, lower latency storage devices, etc., faster network. So they invest in a not a 10 gigabit network, but multiple times 10, like a much faster network than that. And the other group are kind of optimizing for cost, meaning they want to deliver a service that competes against, say, DigitalOcean. They want to deliver that service at a price that is competitive on the market. And in that scenario, they pack many VMs on the same hosts, and there are some strategies for how they optimize these VMs on the hosts. They don't use the latest generation storage hardware. They don't use NVMe drives. They use SATA SSDs, for example. They don't use like 25 or 50 gigabit network. They use a 10 gigabit network because it is a lot cheaper and gives you kind of most of the benefit, not all the benefit, but it gives you most of the benefit and enables you to deliver a particular service level. So it's kind of depends. I would start with defining what kind of where I want to fit in the market in terms of price performance, and then go from there.
Okay. You mentioned network already. That partly answers the next question from Michael. I come to Speicherstief's questions quite later, but Michael also asked, you mentioned storage as one of the main factors with a high performance impact. What do you consider are the other factors that leads to this high difference you see in public cloud performance?
Yeah, so the other is the second top factor. So if you think storage is number one, specifically storage latency is number one, right? The second one I would think is the per core performance you can get. So these are things like large CPU caches, high CPU frequency, things like that. Then the reason on this specific benchmark, the reason this line is so far to the left is storage latency. The reason this line is so far high is storage throughput. So it's how many IOPS can the storage deliver to a single virtual machine. In this case, we are able to deliver more than 100,000 IOPS to one VM, right? And obviously, you also need, if you're delivering that much performance to a single VM, you need a storage system that is kind of can deliver millions of IOPS per second, and in a kind of large environment can deliver tens of millions of IOPS per second, because you're kind of promising every customer that they would be able to get 100,000 IOPS. So how high this line goes is kind of CPU frequency as well as storage throughput, IOPS per VM, and how far to the left this line goes is storage latency. Kind of these are the main drivers.
Finally, it all depends on the whole systems. Using SSDs with a traditional classic SATA interface isn't as performant as using it with NVMe or just the network using InfiniBand versus fiber channel over Ethernet or something like that. So it all depends on the whole infrastructure.
There are, okay. I want to kind of point out that it is IT infrastructure is a complex system, meaning it's very hard to predict what effect would one change have. So, for example, if in this scenario we found that there is a new model of SSD that is 20% lower latency, I have no idea, absolutely no idea, how that would affect this benchmark, right? Would it move it to 0.8? Would it move it to 0.9? I really don't know, and I have no way of calculating that, because it's a complex system. There are a lot of things kind of influencing each other, and the only way to get a result is to measure, right?
Yeah, that's reasonable. Okay, so last questions. Speicherstief. Oh, he came too late. Speicherstief came late. He didn't follow the talk from the very beginning. But did you run your code benchmarks, your cloud benchmarks completely in the public clouds, or was just storage in the cloud and the service in some on-prem infrastructure?
So these are, I'm going to go there, right? So these are, all the tests I present here are virtual machines and block storage in the same region.
Okay.
And this would be kind of very typical for how, so these are like virtual machines and virtual disks, and they are fairly close to the virtual machines, as close as we can get.
We will send Speicherstief the presentation, and then he can read everything he wanted to ask because he was late. The next question here is, what do you think are general benefits of software-defined storage compared to legacy storage area network storage?
All right, very kind of common question. The performance benefits we discussed here, it's possible to achieve them with a traditional storage system. It's possible to achieve them with a software-defined storage system. So performance by itself is not like a benefit of software-defined storage. The benefits of software-defined storage are others. One very important benefit of software-defined storage is the lack of hardware lock-in. So the servers you use to run a software-defined storage system are standard x86 servers that you get from your usual server supplier, be that with an Intel CPU or AMD CPU, Dell, HP, IBM, Lenovo, etc., right? Another benefit is that because kind of the software, the intelligence of the software system is of the storage system is in the software layer, and it's not like a specialized appliance. You have complete freedom to replace that hardware over time. Meaning, If your replacement cycle for servers is 4 years, at the fourth year, you can keep, without even restarting your workload, you can keep that storage system running and gradually replace the servers underneath, right? And in a traditional storage environment, that's a migration project, right? In software-defined storage, this is kind of an assumed benefit, and most storage systems, software-defined storage systems, aim to have that, right? And I said it's standard server. It also means, in our case, in the case of many software-defined storage systems, this is a standard Linux operating system that you can deploy and monitor, etc., using the tools you use for all of your other servers. Like, it's not something like a complete unique type of piece of infrastructure. It's a Linux server, right? So there's some consolidation on the kind of monitoring and management side.
Okay, even more benefits for businesses. Okay, Quen, thank you very much.